Hello students, good evening. Hope you all doing good. So hope your JEE exams went well. Okay, yeah. So we have been studying atomic structure, right? We already have completed our first chapter, that is some basic concepts, and now we have moved to atomic structure, and I think we have completed 3 topics or 2 topics we have already completed from atomic structure. And today we are going to discuss a new topic from atomic structure, and we'll get into that. Before going into the topic, I welcome you all to the APJ Academy. Yes, now I would like to inform you about our full year course, and you can see on your screen our full year course. Okay, what all we provide, and the amazing feature is that we provide all these for 1 year for just rupees 490 per month. Okay, you can crack a JEE or NEET with this enormous discount. That's one of the best thing you can ever have in the online courses. Okay, now, and if you are new to this channel, if you are listening or watching this for the first time, you can subscribe to our YouTube channel. And why you have to subscribe is that we are giving quality content in the YouTube channel, and that is for free. So it will always add value to your preparation. So you can subscribe to our YouTube channel. And that's all about me. And you can read what all credentials I have. I'm a Tech holder and a National Olympiad winner with 6 years of experience in this field. And I have guided more than 1 lakh students to crack the exam, and I've created many wonderful ranks in the sphere of JEE as well as in the sphere of NEET as well. So today we are going to discuss about the wave mechanical model of an atom. Okay, this is what we are going to discuss here, and we already have discussed Bohr atomic model, and we also have discussed about the applications of Bohr atomic model. That is the hydrogen spectrum, the absorption spectrum, the emission spectrum, and we have done number of problems regarding that. And if you have watched those classes, I hope everything was clear for you, right? Now we are moving towards the next mechanical model or the next atomic model, that is a wave mechanical model, which is way more advanced one than the Bohr atomic model. Okay, we know that Bohr atomic model have certain limitations, and wave mechanical model have to an extent have covered those limitations. So let's start with these with this topic. And in wave mechanical model, basically you have 2 concepts to study. Okay, both are very important. When you check the previous year questions, you can see certain questions have asked from de-broglie concept and also from Heisenberg's uncertainty principle. So it's an important topic, and here you have to understand is that this wave mechanical model consists of 2 concepts. Okay, one is de-broglie concept, that is dual nature of matter. De Broglie is the scientist who have brought the concept of dual nature. Okay, the matter have dual nature. First of all, he understood, or he discovered, that the electron have dual nature. Okay, electron not only have, since it has mass, since electron has mass, so anything which has mass will show particle nature. That's a known fact. But de Broglie also discovered that it also have wave nature. Okay, wave nature means it not only moves parallel, it not only have translatory motion, that means it also have vibratory motion along with the translatory motion. Okay, it shows what? It shows wave nature along with the particle nature. That's what de Broglie told. Okay, we will discuss it in detail. Then we have the another one is Heisenberg's uncertainty principle. See, Bohr has told that we can find electron in certain orbits which have nh by 2 pi angular momentum of nh by 2 pi, the orbits which have the angular momentum corresponding to nh by 2 pi, we can find electrons. But what Heisenberg has told that we can never find an electron in the exact positions. We cannot predict the exact position of electron. He told that simultaneously we cannot predict the exact position or location of electron. Either means position or velocity of electron. Either you can exactly predict the velocity of electron, but at the same time you cannot find the electron's position. If you are finding the electron's position, then at the same time you cannot measure the exact velocity of that electron. So this is what Heisenberg uncertainty principle says. So if we cannot exactly locate the position of electron, then there is a problem with the Bohr's concept. Bohr have told that the electrons is revolving around the in orbits which is having a specific angular momentum of nh by 2 pi, but Heisenberg is telling that it's not possible. If you can clearly predict, or if you can clearly say that the electron is in this particular orbit, then Heisenberg principle is wrong. But that even Bohr cannot say that. So we go with Heisenberg's uncertainty principle, that is better than Bohr's model or better than Bohr's concept of this orbits. What Heisenberg's told is the correct one. Okay. At the same time, we cannot measure the value or locate the position of electron. Measure the value of velocity. Okay. The velocity as well as the position cannot be simultaneously located or find out for a particular electron. That's what Heisenberg told. We will discuss that in detail. Okay. Now, coming to the dual nature of matter. In dual nature of matter, you can read it here that yes, in 1924, a French scientist whose name is Louis de Broglie, he suggested that if the nature of light is both that of a particle and a wave. See, de Broglie is suggesting that if the nature of light is both particle as well as wave, that means we know that the nature of light is both particle as well as wave nature. Since it has wave nature, that is why the interference of waves and the double slit experiment and all you have studied, you might have studied in your physics classes, or you will be studying it in the physics classes, the diffraction and all. These diffraction effect and all is shown by the light because it has wave nature. So that's not our topic, so I'm not going into that. So we know that the light have both particle as well as wave nature. Okay. So let me rub this. Okay. Otherwise it will be difficult for you to read it, right? Okay. So it has particle as well as it has wave nature. Okay. And this dual behavior should be true for the matter also. This is what de Broglie said. If a light is having, or if a photon is having particle as well as wave nature, then it should be true for all the matter to have this nature. That is what nature? That is particle nature as well as wave nature. So this is what de Broglie said. So he also find out that the electron is showing particle nature as well as wave nature. So if an electron is showing that, then obviously all the matter also will have the particle as well as the wave nature. So corresponding to the particle nature, we know that the energy of the particle will be equal to E is equal to mc square. That is the equation which Einstein have put forward. And if a matter is having wave nature, then the energy will be corresponding to hc by lambda, and where lambda is the wavelength of the particular wave. Okay. So E is equal to mc square if the particle for the energy corresponding to the particle nature, and E is equal to hc by lambda, the energy corresponding to the wave nature. So for a particular matter, the particle nature and the wave nature should be equal. So when we equate this, mc square is equal to hc by lambda, the energy will be same for a particular matter. So mc square is equal to hc by lambda. I can cancel this c from both the RHS and LHS. So we get it as mc is equal to h by lambda. That means lambda is equal to h by mc. And we know that c is the velocity of light in vacuum. So we are not discussing anything regards to vacuum. So I replace the c with v. V is velocity in any medium. Velocity in any medium. Velocity in any medium. So what is the value of lambda? Lambda is the wavelength, and wavelength is equal to h by mv. What is h? H is the Planck's constant that we have discussed earlier, and m is the mass of the matter. If you are considering about the electron, then mass of the electron, and v is the velocity of that electron in the particular medium in which the electron travels. Okay, so we can find out the wavelength lambda by using this formula h by mv. How we found out this lambda value? By connecting both the nature, the dual nature of matter, that is by connecting the equation of energy of the particle nature as well as by connecting the equation of energy of the wave nature. By equating both, we got the value lambda is equal to h by mv. Next. Now from here, this is a very important relation which will help you to score marks in the numerical questions which can be asked from this section. That is, we know that we have already found that lambda is equal to h by mv, and we know that mv is equal to corresponds to linear momentum, so that I can replace it by p. P is what? P is linear momentum, so I can write it as h by p. And here we know that kinetic energy is equal to half mv square. Okay, so half mv square, corresponding to that I can and also momentum can be represented as momentum is equal to root of 2m ke. It is not important how I got it. If you want to know, then just apply the value ke is equal to half mv square. Then if you can put the value half mv square, you can cancel it and you will get m into v square. That you will be getting it as m p. Okay, then that is equal to h by root of 2m qv. Here q means the charge of the particle and v is the potential difference. This is very important. It's not the velocity, it's the potential difference v. It's the potential difference v, and remember, it's not velocity. Here it is velocity, but here it is potential difference. Here q means the charge. Okay, so here you can see that when a charged particle carrying q coulomb accelerated by applying a potential difference v, then kinetic energy is equal to qv joule. Kinetic energy is equal to ke is equal to qv. Okay, that's why we gave, instead of ke, I can replace it with qv. So we got a new equation, that h by root of 2m qv. So remember this equation. Now for electron, after applying the values of electron, after applying the values of the constants, we know that this is Planck's constant, which is equal to 6.63 into 10 raised to minus 34. And here mass of electron is 9.1 into 10 raised to minus 31 kilogram, and q is equal to 1.6 into 10 raised to minus 19 coulomb. And likewise, all the constants, we gave the values of constants and we simplified the equation, and we got, for an electron, we can write the wavelength lambda is equal to root of 150 by v, where v is the potential difference, we get the value in Armstrong. Armstrong also we have discussed, 1 Armstrong is equal to 10 raised to minus 10 meter. 10 raised to minus 10 meter. And you can again reduce it to this formula, that is root 150 is equivalent to 12.27. So 12.27 by root v Armstrong. And remember, this v is the potential difference and it is not the velocity. Always remember that v here is potential difference and it's not the velocity. So we'll move on to the next one. Here you have to note that de Broglie hypothesis, it's an hypothesis and it is applicable to macroscopic as well as microscopic objects. You have to remember this. It is equivalent to macroscopic as well as microscopic objects. What do you mean by macroscopic? Macroscopic means that has large mass. See, but if you are applying de Broglie concept to a macroscopic object, we know that macroscopic object is having large mass. So that means if you are considering me, I am sitting here, I am walking, I may run, but you will never see a wave nature in me. But what de Broglie says is that his hypothesis is applicable for microscopic as well as macroscopic. So it should be applicable to me also. Right? I am a microscopic body with 85 to 90 kg. Okay, mass. So why we cannot see or we cannot visually understand the de Broglie hypothesis in macroscopic bodies? Here is the explanation. You see, in the macroscopic body, we know that the mass is very large. If the mass is very large, then obviously what will be very small? The wavelength will be very small. If the wavelength is so small that you cannot even see the wave nature. That's why we say that there is no physical significance for macroscopic objects. If you are considering a macroscopic objects, there is no physical significance. Why? Because for a larger body, for a larger mass body, the wavelength will be very small. If the wavelength is very small, then we cannot even physically find or physically see the wave nature in that particular body. So if the mass is so small, then the wavelength is so large, then we can easily identify the wave nature in that body. Okay, that's what you have to remember here. Clear? Okay. Now, the wave nature of electron was verified experimentally by two scientists, namely Davison and Germer. Davison and Germer are the two scientists who have experimentally verified that the electron is having what? Electron is having wave nature. We know that electron is having particle nature, but electron is having wave nature has been verified by Davison and Germer by carrying out diffraction experiment. Okay, they did diffraction experiment and they found out that yes, electron is having wave nature. Okay. Now the next one. Now Bohr theory and de Broglie concept. That's what we are going to discuss next. Okay. Considering what Bohr said is that Bohr said the electron will orbit in those particular orbit or the orbit or the shell which have an angular momentum of h by 2 pi, right? And we have given that equation mvr is equal to nh by 2 pi. The n value should be integer, so integral multiple of h by 2 pi. And similarly, from this we can say that mv is equal to, we can take that r to LHS and write it as nh by 2 pi r. Let's this be the equation number 1. Okay. And we know that from the de Broglie concept, we know that lambda is equal to h by mv. H by mv. And we can, and this is the de Broglie concept. Okay. And this can be written as the equation number 2. Okay. And by equating 1 and 2, we will get the value, that is mv is equal to h by lambda. Now equating these two equations, we get it as nh by 2 pi r is equal to h by lambda. We can cancel this h and h, and now we get it as n lambda is equal to 2 pi r. N lambda equal to 2 pi r. So this is the equation which you have to learn. N lambda is equal to 2 pi r, where you know that 2 pi r is the circumference of the orbit. So that circumference is equal to n lambda. Circumference is equal to n lambda. Circumference is equal to n lambda. So what does it mean? See, according to Bohr, the electron is orbiting in a circular orbit, and according to de Broglie, the electron is not linearly orbiting, it is orbiting like a wave. So it is moving like this. Okay, so 1 lambda means 1 wave. You have to consider what is lambda. Lambda is equal to the distance between two corresponding troughs of the wave or two corresponding crests of the wave. So trough is the topmost position, like this upper wave, and this lower wave is called as a crest, and this is 1 lambda. So 1 wave corresponds to 1 lambda. So in the first orbit, if you are considering the first orbit, here what do you mean by n? Let me clear that. What do you mean by n? N is equal to the number of orbit. Okay, n indicates the number of orbit. So here in first orbit, if you are considering first orbit means the first shell. In first orbit, n is equal to 1. So what will be the value of 2 pi r? 2 pi r is equal to 1 lambda. So in the second one, that is in second orbit, n will be equal to 2. That means 2 pi r, the circumference will be equal to 2 lambda. That will be equal to, lambda is the wavelength, and that means 2 lambdas or the 2 wavelength will cover the whole circumference of the second orbit, or just the 1 wavelength is enough to cover the first orbit. 2 wavelength is required to cover the second orbit. Likewise, if you increase the value, if you are moving away from the nucleus, that means if you are in the third orbit, for third orbit what will be the how many waves should we require? We require 3 waves. Okay, for fourth orbit we require 4 waves to complete the circumference. So the equation is so simple. If you are asked in the question, for covering 1 orbit, how many waves are required for an electron to cover that? Just 1 wave is required to cover the complete circumference of the first orbit for an electron. For the second orbit, it requires 2 waves. Okay, here you can see this is just 1 wave. Okay, the distance between the two corresponding crest or trough is the wavelength, or 1 lambda is equal to 1 wave. So just with 1 wave, an electron cover the first orbit. With 2 waves, it can cover the second orbit. With 3 waves, it can cover the third orbit. Likewise, it goes. So this concept should be very clear. We are collaborating both the concept, that is Bohr theory, as well as the de Broglie concept. So n lambda is equal to 2 pi r is the equation you have to remember here. If you are considering the first orbit, you only require 1 wave. For second orbit, the electron requires 2 waves to cover that whole circumference. For third orbit, it requires 3 waves to cover the whole circumference. That's what this theory and that's what this part of the concept is explaining to us. Hope this is clear, students. So 2 pi r is equal to n lambda is a very important equation. You have to learn that. Now coming to the problem, a body of mass 20 gram is moving with velocity. So body is having a mass of 20 gram. It's moving with the velocity of 500 meter per second. Find its de Broglie wavelength. Okay, de Broglie wavelength, we know the equation lambda is equal to h by mv. So everything is given in the question. So just give the value. 6.62 into 10 raised to minus 34 is the de Broglie value. And mass should be taken in kilograms. So 20 into 10 raised to minus 3 into 500. So you can just calculate this, cancel this, you will be getting 10 raised to minus 31. Again, you can cancel these 3 zeros and it will become 10 raised to minus 28. No, it will become 10 raised to minus 34. Okay, you cannot cancel, it will go to the top. Okay, it is 10 raised to 3. So 10 raised to 3 and 10 raised to minus 3, you can cancel it here, right? So that is a better option. So let me rub this. So 6.62 into 10 raised to minus 34 divided by mv, 20 into 10 raised to minus 3 into 500. So these two zeros, 1 0, total 3 0, 10 raised to minus 3 can be cancelled. So this is 2 into 5 is 10. So you will get an answer as 6.62 into 10 raised to minus 34 divided by 10. That means 6.62 into 10 raised to minus 35. Okay, that much meter will be the wavelength of the de Broglie wavelength. Okay, so hope this is clear. Now let's move on to the next one. Calculate the de Broglie wavelength lambda of electron present in the third orbit of hydrogen atom. Okay, in the third orbit. So here you have to use the equation that we have just derived, that is by collaborating the equation of de Broglie and as well as Bohr. So that's the easiest way to do it. 2 pi r is equal to n lambda. Here n is 3, so lambda is equal to 2 pi r by 3. Okay, you get it here as 2 pi r is equal to 3 lambda and lambda is equal to 2 pi r by 3. Now, what is the value of r? We have studied in the previous session that r is equal to 0.529 into n square by z. Here it is given that third orbit, so you can substitute n value here. 0.529 into 3 square, that is 9, divided by z, atomic number of hydrogen is 1. So 0.529 into 9. So we can substitute the value of r in this equation and you will get it as lambda is equal to 2 into 3.14 into 0.529 into 9 divided by 3. This you can cancel and the total answer you will be getting equal to 9.96 Armstrong, that is nearly equal to 10 Armstrong. Okay, so this is the easy way to do the problem. Very good problem, you can just note it down. Now we'll move on to the next question. Students, hope this is clear for you. If you have any doubt, you can just type it in the comment section so that I can reply to you. Okay, right. Now we'll move on to the next question. See, two particles A and B are in motion. Lambda A, wavelength is given, lambda A, that is the wavelength of A, and mass of B is 25% of mass of particle A. So see, mass of B is equal to 25% of particle A, 25 by 100 into mass of A, that is equal to 1 by 4. So mass of A 1 by 4, 25 by 100 is 1 by 4. So mass of B equal to MA by 4. And similarly, the velocity of B is 50% of A. Velocity of B is 50% of A. Velocity of A, that is VA by 2. Okay, right. So you have to calculate the lambda of particle B. Let's take the ratio, that is I'll write it here. Lambda A is equal to MA into VA divided by lambda B, that is equal to MB into VB. We know the value of lambda A, that is 4 into 10 raised to minus 5. Okay, and MA into VA, it is divided by lambda B. What is MB? MB is equal to MA by 4. So MA by 4. What is VB? VB is VA by 2. Cancel MA VA, cancel MA VA. This will be 8. It will go to the numerator. So 4 into 10 raised to minus 5 by lambda B is equal to 8. So lambda B is equal to 4 into 10 raised to minus 5 divided by 8. So you can cancel it with 2. So you will be getting 0.5 into 10 raised to minus 5. 0.5 into 10 raised to minus 5. Hope this is clear, students. Yes. So here I made a mistake, that is lambda A is equal to h by mv, right? So here I made a big mistake, that here, let me correct it. Okay, I just wrote the lambda A is equal to h by MAVA. Similarly, lambda B equal to h by MBVB. So we get it as MBVB divided by MAVA. This h and this h will get cancelled. So this is the equation. So I just got it wrong there. Now you can just apply the values. By applying the values, lambda is already given, that is 4 into 10 raised to minus 5, 10 raised to minus 5, divided by lambda B equal to, what is MB? MB is MA by 4 into VB is VA by 2 divided by MAVA. You can cancel MAVA. So you will be getting lambda 4 into 10 raised to minus 5 by lambda B is equal to 1 by 8. So you will be getting lambda B equal to 3.2, 32, 4 into 8, 8 into 4 is 32 into 10 raised to minus 5. So 32 into 10 raised to minus 5 meter will be the answer of lambda B. Okay, so previously I did a mistake, that instead of h by mv I just wrote it mv. That was a big mistake, so be aware of that. So we just made the rectification and we got the value as 32 into 10 raised to minus 5. If you want to write it in terms of 3.2, then you can write it as 3.2 into 10 raised to minus 4 meter. Okay, yes, now we will move on to the next one. An electron has kinetic energy. Yes, kinetic energy is given as 2.8 into 10 raised to minus 23 joules. 2.8 into 10 raised to minus 23 joules. We have to find out the de Broglie wavelength. We know the equation lambda is equal to h by root of 2m AE. Since it is electron, we know the mass and kinetic energy value has been given. H is constant. So by applying all the values, we get it as 6.63 into 10 raised to minus 34 divided by root of 2 into mass of electron is 9.1 into 10 raised to minus 31 kilogram into kinetic energy is 2.8 into 10 raised to minus 23 joule. Okay, so you will be getting 6.63 into 10 raised to minus 34 divided by multiplying this value 2 into 9.1 into 2.8, we will be getting a value nearly equal to 51. So 51 into 10 raised to minus 31 and 23 is 10 raised to minus 54. Okay, so we can just take out the value, that is 51. If you take the root, we know that the root 7, root 49 is 7. So it is nearly equal to 7 point something. So I can just write 7.2 or something like that, because since in chemistry we will have options with large differences. So we can, for the nearer values, we can just approximate the values in order to find the answer. So it is not necessary that we require accurate values, since the options will have different values. So I just take it as 7 into 10 raised to minus 27. You take the root, it will be 27. So now by dividing it, we get the value as 9.27 into lambda will be equal to 9.27 into 10 raised to minus 8 meter. So calculation part is yours and you have to do it well. Hope you need to practice more. Okay, so that you can easily do solve the problems within seconds. Okay, calculation is your part. You have to do it more and more, practice more and more questions so that you can easily solve the problems. Okay, now we'll move on to the next question. Calculate the wavelength of an electron moving under a potential difference of 1.5 volt. So see, regarding the potential difference, we know the equation, that is lambda is equal to root of 150 by potential difference, that is 1.5, and we get the value in Armstrong. Okay, so here 150 by 1.5 means it is equal to 100, so root 100 we will get, root 100. So what is root 100 is 10, so 10 Armstrong is the answer. So simple as that. So it is, why we got it so simply, because we know the formula, lambda is equal to root of 150 by volt by potential difference, right? We have studied that lambda is equal to 150 by V, potential difference. So applying the value, straightly we got the answer in just 2 steps. Okay. Now coming to the next topic, that is Heisenberg's uncertainty principle. So this is the last topic for today. See students, I already told what Heisenberg uncertainty principle is. That uncertainty means it is not certain, it is not sure. So what is not sure? Heisenberg is telling that if you are sure about the position, then you are unsure about the momentum of that particle. Once if you are sure, see, momentum means actually we are aiming at the velocity, because mass is constant. Momentum, we know that momentum P is equal to mv. So mass is constant. What is varying? Velocity is varying. So we are uncertain about the velocity. Sorry for that. If you are certain about the velocity, then the position is uncertain. So what Bohr said is that Bohr taught us the ways to calculate the velocity, accurate velocity. Bohr also told that the electron movement is in this, that is in an orbit of nh by 2 pi. So what Heisenberg is telling, no, that cannot be true, that cannot be accurate. And we know that Bohr also didn't explain how he got the value nh by 2 pi, how he took the orbit's angular momentum as nh by 2 pi. He didn't explain that. And Heisenberg is telling that if you know the velocity of electron, then it is sure that you cannot exactly position the electron, or it is unsure that you, or it is uncertain about the velocity or the position of the electron if you are certain about the velocity. Similarly, vice versa. If you are certain about the position, then you are uncertain about the momentum or the velocity of the electron. That is what Heisenberg uncertainty principle all about. So it is impossible to measure simultaneously. What do you mean by simultaneously? Simultaneously means at the same time. It is impossible to measure simultaneously the exact position and momentum of a microscopic particle. So you cannot measure simultaneously the exact position or the exact momentum or the velocity of the particle, of microscopic particle. Okay. Yes, students. So coming to the equations. So what Heisenberg told is that delta x, that is the uncertainty in position, into delta p is greater than or equal to h by 4 pi. What is delta x? Delta x is uncertainty in position. Uncertainty in position. What is delta p? Delta p is uncertainty in momentum. Uncertainty in momentum. Okay. So I can write it as delta x into, instead of momentum I can write it as mv, but m is constant, v is uncertain, so I can write it as m delta v greater than or equal to h by 4 pi. I can write it as delta x into delta v greater than or equal to h by 4 pi m. Okay, these equations are very important, you have to study it. Okay, and similarly I also wanted to give you another uncertainty equation based on Heisenberg principle, that is delta E into delta T is greater than or equal to h by 4 pi. What is delta E? Delta E is uncertainty in energy. Uncertainty in energy. See students, this equation is not known by many of the students, and with this equation there are numerous questions have been asked in JEE Advanced. Okay, so you have to be aware of this, and being part of APJ Academy you have to know this. I've already told you we are giving you a classic content that is for free. Okay, so delta E dot delta T is greater than or equal to h by 4 pi, and delta T is uncertainty in time. Uncertainty in time. So all these equations are important. These equations you will normally see in the textbook. Okay, all these equations are important. Especially you have to be aware of this equation, delta E dot delta T greater than or equal to h by 4 pi. Clear? Next one. What happened, Vijay? How many students watch live? Winners are only just 1% students. You know that. In the JEE exam or the NEET exam, if you consider, there will be only 1% student will qualify that. And that 1% will not be available for everything, right? So see here is a question. The uncertainty in momentum of a moving electron is 10 raised to minus 15 kilogram meter per second. Calculate the uncertainty in its position and velocity. You have to calculate the uncertainty in position as well as in velocity. So can you do this problem? Yes, we know that delta x dot delta p is greater than or equal to h by 4 pi. So here the momentum is given 10 raised to minus 15. You have to calculate the position as well as velocity. Okay, so let's calculate it. Delta x is greater than or equal to h by 4 pi into delta p. Okay, and let me give you this the simple trick, that is h by 4 pi. You just remember this value, that is 0.527 into 10 raised to minus 34 joule second, or it is equal to 0.527 into 10 raised to minus 27 erg second. Okay, so this will make your calculation much more simpler. Okay, 0.527 into 10 raised to minus 34 joule second. So just substitute the value. Delta x will be greater than or equal to 0.527 into 10 raised to minus 34 divided by 10 raised to minus 15, that is already given in the question. So you'll get the value as 0.527 into 10 raised to minus 19 meter. That is a uncertainty in position. And see, we are also asked to find out the uncertainty in velocity. How to find the uncertainty in velocity? We know that delta p means m delta v. Delta p is 10 raised to minus 15. Since it is electron, we know the mass, right? Mass of electron is 9.1 into 10 raised to minus 31 kilogram into delta v. So from here you can find the value of delta v, that is equal to 10 raised to minus 15 divided by 9.1 into 10 raised to minus 31. That's all. That much meter per second. So the value will be equal to, delta v value will be equal to 1.09 into 10 raised to 15 meter per second. Hope this is clear, students. Okay, so in the first question you are asked to find out the delta x, the position, and then you are asked to find out the velocity, uncertainty in velocity. So from using the equation delta x dot delta p greater than or equal to h by 4 pi, and you got the value as 0.527 into 10 raised to minus 19 meter, that is for delta x, uncertainty in position. And then you move on to find delta v, that is we know the equation delta p equal to m delta v, and that is delta V equal to 10 raised to minus 15 by 9.1 into 10 raised to minus 31. So we got the answer 1.09 into 10 raised to 15 meter per second. Okay, now the next question. If the uncertainty in velocity and position is same, then find the uncertainty in momentum in terms of mass. See here again, we know the equation delta x dot delta V equal to h by 4 pi m. So since you have to find out in terms of mass, I use the second equation. Okay. Now we know that since delta x is equal to delta V, because uncertainty in velocity and position is given as same, you can just apply it here. Instead of delta x, I am going to use delta V. So delta V into delta V equal to h by 4 pi m. Right? So we got it as delta V whole square is equal to h by 4 pi m. That means delta V equal to root of h by 4 pi m. Now you are asked to find out the uncertainty in momentum in terms of mass. So momentum delta P is equal to m delta V. Substituting the value of delta V, we get it as m into h by 4 pi m. Okay, and you can cancel this and this will become root m. So the value will be equal to delta P equal to root of mh by 4 pi. As simple as that. Right? It's a very good question. So the next one. Okay. This is very important question. These model questions have been continuously asked in JEE mains as well as in NEET also. A particle has a mass of, so mass is given 10 raised to minus 10 gram. Okay, and velocity is given in 10 raised to minus 6 centimeter per second. If the error in the measurement of velocity is 0.0001%, then calculate the uncertainty in its position. So percentage error in velocity is equal to delta V by V into 100. This is how you find out the percentage error. Okay. From here, see, this is given only to find out the value of delta V. So this is a very good question. Okay. So if you do not know this relation, then you are never going to do this problem. Instead of giving directly the uncertainty in velocity, they gave it in terms of error in measurement. Okay. So error in the measurement is equal to delta V, that is, if you are considering the velocity, then delta V by V into 100 give you the error in the measurement. Okay. So now just apply the value, that is percentage error is given as 0.0001 by 100, that is by 100 into 10 raised to minus 6 will give you delta V. So delta V equal to percentage error into V by 100. So percentage error into V divided by 100. So you get the value as delta V is equal to 10 raised to this is 10 raised to minus 4, this is 10 raised to minus 6, this is 10 raised to 2. So in total you will be getting 10 raised to minus 12 centimeter per second. That is the value of delta V. So we got the value delta V. Now you have to find out delta P, right? Calculate the uncertainty in position. So write the equation that delta x dot delta V equal to h by 4 pi m. So here we know that delta x is equal to h by 4 pi m delta V. That is equal to h value is, I have already told you, it is 5.27 into 10 raised to minus 27 divided by 4 into 4 pi m, 4 into 3.14 into, what is the value of, m? Mass is given as 10 raised to minus 10. Yes. Now you can calculate this. You will be getting a value that is nearly equal to 4 into 3.14 is 4 pi m into delta V. Where is delta V? We have find out the value of delta V, that is 10 raised to minus 12. Okay, 10 raised to minus 12. Okay. So comparing these values, this 10 raised to minus 10 into 10 raised to minus 12, you can just calculate it. I have just find out the near value, that is delta x is equal to 5.27 into 10 raised to minus 6 centimeter. Is near equal to 5.27 into 10 raised to minus 6 centimeter. Okay. So this is the answer of delta x. Hope this is clear, students. Okay. What we have done is that h by 4, we know the equation delta x into delta v equal to h by 4 pi m, and delta x is equal to, we are asked to calculate the uncertainty in position. So h by 4 pi m into delta v, h value 0.52, sorry, here we, here I made a mistake. See here, this is not required, because we already found out that h by 4 pi is equal to 0.527 into 10 raised to minus 27. So I have already given the value 0.527 into 10 raised to 27, that corresponds to h by 4 pi. Okay. Now we only have to write these two values. That is the value of mass and delta V, these two values. That is 10 raised to minus 10 into 10 raised to minus 12. Okay. So we get the value equal to 5.27 into 10 raised to minus 6, that much centimeter. So this one has helped us a lot, right? H by 4 pi is equal to 0.527 into 10 raised to minus 27. Hope this is clear, students. Yes, please let me know in the comment section. Okay. So this is all about our today's lecture. We have discussed the wave mechanical model. In that, two major concepts, that is Heisenberg's uncertainty principle and de-broglie's dual nature of matter. We discussed the theory in detail, and also we have done a very good number of questions, and which are most important questions covering the total concept of these two topics. And this question which you are seeing on the screen is very important question. This is a type of question which is normally asked in JEE mains. Okay. So from this section, particularly from this section, because instead of giving you the uncertainty in velocity, they have given you the error. Okay. So error. So it is from the chapter, some basic concepts you might have studied the error calculation, or from the practical classes, or from physics, from the first chapter you study about the error, measurement, the error occur in measurement, and that equation, the percentage error, is calculated as, if it is in velocity or if in any other terms, it is delta V by V into 100. So from this equation only you will get the value of delta V. That's how normally JEE asks the question. Okay. Okay. So this is it. So hope this is clear, students. So with this, we will be having one more topic from this atomic structure, that is with respect to quantum numbers, that will be discussing in the next class. Hope this class is helpful for you. We will meet in the next class. Until then, bye bye. Take care.